Am I audible?
Yes, you are audible.
That hasn't joined in. Let's wait for some more time.
Yes. Hello.
Yeah, hello. Welcome to our fourth winter school. Yeah, we'll start soon. Just wait 2 or 3 minutes more to join more candidates.
Sounds good. I think I'll need permission to share screen.
Yes, yes. Let me co-host to you. Yeah, you are now co-host now. Please share. You can share your screen now.
Should be visible, I hope.
Yes, yes. Screen is visible, and can you change the slides? One or two slides, just. Yes, yes. Slides are also changing. It's working fine.
Yeah, wonderful.
Sir, should we start now or wait for uh, another
Hello,
couple
Peter.
of minutes?
Hello, Peter. Thank you for joining us this year as well.
Yeah. Thanks for having me.
Great to have you always. Uh, I think we can start. Okay, so Kushal, you can.
This meeting is being recorded.
Uh, uh, you can read the bio, sir. You can.
Yeah, I can
Yes, yes,
start formally by introducing
yes.
our speaker.
Introduce Peter to the audience.
Yeah. So, good afternoon, everyone. We are starting this first plenary lecture for Winter School on Deep Learning WSDL 2025 this year. And we are thrilled to have Dr. Petar Veličković with us today. Uh, Dr. Petar Veličković is a staff research scientist at the senior level at Google DeepMind, an affiliated lecturer at the University of Cambridge, and an associate of the Clare Hall, Cambridge. He earned his PhD in computer science from the University of Cambridge Trinity College under the supervision of Pietro Leo. His research focuses on geometric deep learning, developing neural network architectures that respect the symmetries and invariances in data, a topic he has co-authored a proto-book on. Recognized as an Ellis Scholar in the Geometric Deep Learning Program, Dr. Velickovic specializes in graph representation learning, particularly its applications in algorithmic reasoning, as highlighted in VentureBeat. He is the first author of influential works such as Graph Attention Networks, a widely used graph convolutional layer, and Deep Graph Infomax, a prominent self-supervised learning framework for graphs, and both featured in ZDNet. His research has been instrumental in advancing technologies like travel time prediction for Google Maps, featured in CNBC, Engadget, VentureBeat, CNET, The Verge, and ZDNet, and also aiding mathematicians in discovering groundbreaking theorems and conjectures covered by Nature, Science, Quanta Magazine, New Scientist, The Independent, Sky News, The Sunday Times, La Repubblica, and The Conversation. So, with so much accolades, he comes at a quite as a big rising star in this particular field of geometric deep learning. And now I would request Dr. Velickovic to please take the stage.
All right. Thank you so much, Swagatam, for inviting me for a second year in a row. I have really enjoyed my presentation last year. I am really looking forward to all of the nice interactions we will have today. So once again, hello, everyone. My name is Petar Veličković. I'm a senior staff research scientist at Google DeepMind and affiliate lecturer at the University of Cambridge. Today, we will be talking about the transformer. So one of the currently most popular neural network architectures. We're going to deconstruct how this model works. And from the deconstruction, we are going to try to unravel some of the specific ways in which transformers will almost certainly or even provably underperform on tasks, especially when those tasks require you to reason out of distribution. This is the reason why the title of today's talk is the Transformer Out of Distribution House of Cards. No worries if the 5 cards on this slide don't make a lot of sense. I do have a story tied to each one of them. We will go through them one at a time. They relate to 5 of the recent papers that me and my co-authors have written to try to expose some of these limitations. So we are going to start by just a motivational setup of what do we mean by the House of Cards. So basically, currently we are in a pretty exciting time where transformer-based architectures or neural networks more generally can clearly solve problems that would be demonstrating almost like a PhD level of knowledge, or certainly knowledge in the top percentiles of humans, right? So there are many such accomplishments that you can see just from the previous year. I've highlighted 2 that for me personally resonated the most. The first one is, you might be aware that last year, an artificial intelligence system developed by DeepMind, AlphaProof, participated in the International Mathematical Olympiad, the IMO, which every year gathers the most talented high school students worldwide and sets them mathematical problems that are well out of reach of most humans. And the AI system was able to achieve performance equivalent to a silver medal, which is basically, with the exception of combinatorics tasks, at the level of the highest competitors in this competition. Another accolade you've probably heard about, last year, the Nobel Prize in Chemistry was awarded jointly to David Baker, Demis Hassabis, and John Jumper, and at least 1/2 of this prize has been allocated in recognition of the AlphaFold system, which is an automatic AI system that can predict 3-dimensional fold structures of proteins way better than any previous human-devised methods could. So clearly, these methods are onto something. They're able to attack really, really, really challenging problems. But then you look at the ground rules with which they actually try to solve these problems, and then you actually immediately start to notice cracks in the system. One specific problem, which I always like to highlight because it's kind of inherently tied to the computations the model itself is doing, is, as you probably know, modern transformer architectures often even have hundreds of billions of parameters, right? So and they use those parameters often multiplicatively. So inside the architecture, you have hundreds of billions of multiplications just to generate one part of your output. However, you can ask them to do multiplication. So give them 2 numbers and ask them to perform the multiplication of those 2 numbers. And as soon as those 2 numbers get modestly larger in size, for example, 3-digit numbers, as you can see in this table, the accuracy of predicting the correct result drops drastically. And this is this table here is specifically one of the previous Gemini class models, but this trend holds across all different types of modern frontier language models. Very similar trends hold for models like GPT-4. There is this great paper from Shen et al. From 2023, which investigates this as well. So even though you have this situation where the model is extremely smart in specific narrow questions you ask it, they don't really seem to understand what they're doing, because even if you ask them a simple computational problem, which very nicely aligns with what's inside the model, so the model has a lot of multiplications, it should just set up the input in a particular way and perform the multiplication, yet it's unable to do so reliably. You vary the input a little bit and you suddenly start to see cracks. And this is something that, to me at least, is an extremely interesting scientific problem, something that's very much worth studying. And in this talk, I will take you on a journey of several works that me and my group have published in the previous months and years to try to understand why this happens. And we don't just seek to understand why it happens, we also want to solve it, but we want to solve these problems not just in a kind of aspirational way, because whenever there's a particular computation that a transformer or any other model cannot do, you could just directly embed that computation inside the model and solve the problem that way, right? We don't want to solve the problem that will require us to do something exhaustive or something that doesn't play nicely with gradient descent. We really want solutions that will easily scale to the largest frontier model sizes of today, hundreds of billions of parameters. And what this means is that because we want to understand and we want to analyze the solutions properly, we want to focus, and this is something that's not done as much in modern language model literature, we want to focus as much as possible on proving that certain foundations are flaky. So what this means is that we will explicitly not want to analyze specific failure examples and then conclude the model cannot do this kind of computation, because I feel like when you're doing that, you're just giving away free training data without really teaching us about what the problem is, right? So really, if we've discovered a foundation that is flaky in a transformer model, that means no matter how well you train it, if it's trained under the current procedures of how the architecture is built, I should always be able to use my provably flaky foundation to find an example where your model is going to fail, right? So this is really what we're after, kinds of problems that cannot be fixed no matter how well you try. And this whole concept of taking a computation and then checking whether the model can do meaningfully on variations of that computation is something that we weren't the first ones to do. Actually, it's been pioneered a year or so ago, and I like to dub it the reasoning gap from this landmark paper from Srivastava and others, which basically tries to measure how good is a model at solving math problems or similar problems when you change the input parameters somewhat. So the reasoning gap was the first paper to kind of bring these concepts into our attention. And more recently, it's gotten quite popular, especially with the release of GSM Symbolic, which is another paper, this time from the folks at Apple, trying to show how as you vary the inputs to a mathematical reasoning task, modern LLMs all tend to struggle. And sometimes you can get massive drops in performance just by taking an established problem in a math benchmark that all of these models can solve perfectly and just changing the numbers a little bit, right? So this, for example, if the task is asking you to add up 2 and 7, you can change it to ask to add up 1 and 9 or something like this. These are the kinds of modifications we're talking about. So we're really not changing the essence of the computation that needs to be performed. We're just changing the inputs, the specific inputs on which that computation has to be performed. So I am very, very fond of efforts like these because they really tend to expose to what extent different models really understand the systems that they're operating on. I would say one issue with doing this on top of existing math benchmarks is that basically it's not very easy to scale up these efforts. You have to manually look at the different math problem to make sense of which corrections to the problem make sense. Just to give you a silly example, imagine that the problem requires you to reason about the sides of a triangle. So not every triplet of numbers will give you legitimate sides of a triangle. You need to satisfy the triangle inequality. So you need to kind of, what the folks from the reasoning gap paper did to a large extent is they manually sifted through a lot of these problems, figured out templates, figured out how to generate inputs for those templates, and then scaled that up. But this is an effort that cannot very easily scale up in a drastic way. You always have to like manually analyze the problem and make sure like what are the things you're allowed to do and what are the things you're not allowed to do. So we set out to make our own contribution to address this problem. And actually, we started looking at these kinds of generalizations on how well is a model matching a mechanism well before the language model explosion of 2023. So how can we test? This is the question we can ask ourselves. How can we test if a model truly understands the task that we're asking it to do? Well, one way, if we want to do this purely empirically, right, it's not always easy to analyze the internals of these models. So it's hard to guess exactly what is the function that the model is computing. So our best bet often is to analyze the model empirically on specific examples. And really, to be able to test how well the mechanism is followed, we need to test against a wide variety of data distributions. And this may include distributions that the model has seen during training, but it must include distributions that the model hasn't seen during training, because as you probably know, these models will overfit to their data distributions very, very easily. So as a sort of blanket list of desiderata, you might want to have tasks for which you can generate outputs reliably, efficiently, and for any distribution we care about. And I personally believe that when you collect these three constraints together, this means that your problems that you're evaluating on must be supported by some kind of tractable or polynomial time algorithm. So basically, the very existence of an algorithm is equivalent to being able to efficiently generate data for any distribution of interest. Like, there must exist a procedure that allows you to do that. And when we talk about algorithms, what we mean is any kind of well-defined computational procedure that accomplishes a certain objective. One classical example of an algorithm is insertion sort. So here you can see how insertion sort takes an input list like 52431 and gradually rearranges the elements to obtain a sorted list 1, 2, 3, 4, 5. And the algorithm is the mechanism responsible for gradually adjusting the pointers of this list, as you can see in the picture. And guided by this idea that really the main way to test how well a model generalizes outside of this distribution is to check how well it maps to an algorithm, is what led us to pioneer what is now known as the CLRS benchmark. We took this particular textbook, Introduction to Algorithms, which I imagine will be familiar to some or even most of you, especially those of you who are on a computer science degree. This is, in many universities, the standard textbook with which undergraduate level algorithms and data structures are learned. And many modern day software engineers will basically base their knowledge on the algorithms inside this textbook. And even though it has several thousands of pages of content, it really only has about 90 unique algorithms, which we additionally filtered to a list of 30 that we featured in the benchmark. And as you can see, even though we limit ourselves to only 30 algorithms, they still cover a wide range of skills, such as sorting, searching, greedy algorithms, pathfinding algorithms, or other graph algorithms, string matching, or even geometric algorithms like convex hull. So it really is a very carefully crafted selection of 30 problems. And one thing that's important to note about it, this is work we published at ICML a couple of years back, it's not just one data set. Like, as we said, we need to be able to generate data for arbitrary distributions. So CLRS-30 is actually a data set generator. So you specify the certain properties about the computation you want to match, you implement that computation with some lines of Python, and then the CLRS benchmark can take care of sampling data for that task for any distribution that is valid that you care about. And another thing which is great about it is that to make it more approachable to people who don't know how to build machine learning models that well, it's also a baseline generator. So the model will not just generate data for you, it will also happily generate full neural network architectures that take that data, embed it, process it, decode it into outputs, set up batching, set up loss functions. So in principle, if you want to just see how well some particular neural network will fit this data and reason over it, you don't really need to even write neural network code. CLRS will take care of that for you. And this is a benchmark that we've co-developed over many years and finally released it in 2022. And it's fully open sourced. So if you want to play with it, this GitHub link will give you all of the details you need. So one of the main things we've done in CLRS is we've taken all of these algorithms and we've made sure to process them in a sort of graph structured format, because graphs tend to be a very nice universal abstract data structure for dealing with all different sorts of relational data. So whenever you have data that deals with different objects and potentially the relationships between them, a graph is a pretty good way to structure them. And because CLRS unifies all of these different problems in that shared graph representation, this allows us to try to train one model to execute all 30 of these algorithms. So specifically how this works, or how you imagine this might work, is you take the inputs to your 30 problems. So there might be some sorting problem, some pathfinding problem like Dijkstra's algorithm, or even some geometric problem like finding the convex hull of a set of points. And as we said, you can have these encoder functions that CLRS will set up for you that will map each one of these different inputs into a shared graph space. And once you're in that shared latent space, you can then just use a fixed processor network, so a single graph neural network for all 30 algorithms, run it for some steps, and then based on the embeddings that come out of the processor network, you can predict what is the sorted array, what is the shortest path tree, what is the convex hull. For all of these things, you have a separate decoder function G. And we typically make F and G functions to be relatively simple so that most of the computation power will be forced to go through the processor. And it turns out that you can indeed train an efficient model in this way. And we have accomplished this and published our findings in the log conference a couple years back. And in this work, we have trained a model with a single graph neural network over all of our 30 problems. And you can see its performance in orange over out of distribution graphs. So here, this is not the performance of executing algorithms on the training set. It's on 4 times larger inputs than what you saw in the training set. And in blue, you have that same architecture, but which is separately trained for every single task. So these are the blue ones are single task experts. The orange is a multitask generalist. And you can see that the multitask version is actually quite competitive, not equally in all algorithms. Sometimes it's much better than the single task expert, sometimes it's worse. But when you take the averages, which you can find on the far right, on average, the multitask generalist is quite competitive with the single task experts. And therefore, we have just one model that can really execute all of these 30 algorithms at the same time. And this was quite an exciting result. Since 2022, when we published all of these works, the world has moved very deeply into analyzing data that lives on text space, so language inputs. And we tried our best to keep up with the times and try to take what we learned in CLRS 30 and bring it into the age of transformers and large language models. And this led us to propose the CLRS-Text benchmark, which is an extension on CLRS, which more or less just adds a routine to take all of these nice graphs that CLRS builds internally and print them in a format that's textual and therefore suitable for language models. The CLRS-Text version of the benchmark is also publicly available on GitHub. You just need to go into a subfolder designated for CLRS-Text. So what you might expect CLRS-Text to give you, at least with the basic printing functions we provide you, for, say, the insertion sort trace I showed you before, you'll get text like this. And the green part is the prompt. So that's telling your language model what is the algorithm that needs to be solved, what is the sequence it needs to be solved on. And then you have at your disposal the entire trace of how the algorithm gradually sorts the list into place. And then finally, after the pipe character, you have the final sorted array. And this is typically what we evaluate the model on. So has it been successful at producing this final sorted sequence? Now, one thing which is interesting about mapping everything into text is that now the input is the same across tasks. So whereas previously we needed a separate encoder and decoder function for every single algorithm, in CLRS-Text we can get away with a single language model trained on all of these 30 algorithms at the same time. So we really don't need any separate components per task anymore. So naturally, you might wonder, how do language models perform on this benchmark? And well, showing you all 30 algorithms would take up too much space that I have on the slide. So here is a selection of 8 of them. And don't worry, I'll get into what all of these different lines and dots mean. But looking at the performance, here you can see 8 algorithms. On the x-axis, you have the problem size. So how many nodes in a graph, how many entries in a list. And the y-axis is accuracy. So how accurate is this particular language model at predicting these algorithmic outputs? So the first thing you might notice is that there is a big gap between the green curve, and the green curve is just taking a large off-the-shelf language model and trying to prompt it to solve this problem after giving it a few shots. So this is supposed to be kind of the ceiling performance of a base language model. How well can it solve problems like these? And it turns out it cannot really solve them that well. In this particular case, the base model was Gemini 1.5 Flash. And the blue and the orange lines are actually much smaller models. We took Gemma 2B, which is a 2 billion parameter open source model. And we notice that when we tune these models on these particular tasks, they actually improve a lot in performance. So the fact that there's a big gap between the green curve and the others means that certainly there's lots of interesting knowledge inside these algorithms that currently we cannot encompass in our state-of-the-art models. So there's a clear benefit of fine-tuning, and this means that we're currently not really learning these algorithms in the best possible way. Now I want you to focus more on the blue and orange curves. The blue and orange curves are actually identical models. Okay, the only difference I've made is I've changed the way I inform the model about positions, or if you're more familiar with the architecture, changing the positional embeddings provided to the model. But the architecture is exactly the same. So you might find this to be a little bit crazy, because by doing something as simple as changing the way I tell the model where different positions are in the text, I can find differences that are of the order of 60% or higher. So keep in mind, the y-axis here is from 0 to 100%. So this gap that I'm highlighting here is like 60% difference in performance for a string matching algorithm on a certain size, just by changing the way the model learns about positions. It's pretty impressive. But maybe the most important thing that I want you to zone in on is this sharp drop that you see in virtually all of the algorithms. You might have wondered, what are the red dots at the top of every single plot? So the idea is, when we have these trained models, the blue and the orange curve, we train them on specific sizes of these algorithms, and the sizes we train on are the dots in red, right? And what you can notice almost without fault is that the moment you go beyond the largest red dot, so the largest size I've trained the model to do, I increase the problem size by 1 or 2 elements, and almost immediately, or sometimes really immediately, the performance falls off a cliff. And very often it will even fall towards 0%. So clearly these models, even though they're trained and they're doing better than, say, a base model, they clearly haven't really learned what this mechanism is supposed to be doing, if I can throw them off course so easily just by adding 1 or 2 extra elements to my problem, right? And this is something that's very interesting, and it's going to motivate what we're going to talk about next, where we're going to really dive deep into how modern LLMs process data and how they might be failing at these kind of results. So before we dive into that, I'm just going to give you a quick primer on transformers and how they work. This will be a very high-level overview in case anybody in the audience is not familiar. And even in case you are familiar with how transformers work, it will be useful for you to get a feel for the kind of notation I will personally use to talk about them. So the title of our talk is A House of Cards. So A transformer, as you might know, operates as a next token predictor. So you give it a sequence of tokens, which for our purpose we'll just treat as words, even though in reality they're not always words. They might be parts of words as well. And we give it something like a house off, and it's asked to predict the next word, which in this case will be cards. So what happens here is we first embed each one of these tokens in a high-dimensional real valued space. So you have a separate vector learned for the word a separate vector learned for house, and a separate vector learned for off. Then two processes interchange once you've done this for several steps. The first thing that happens is we learn something more about the representation of each word by feeding it through a feed-forward network. This feed-forward network is any kind of standard multi-layer perceptron architecture, so any kind of deep neural network, for example, this particular equation here, which is a two-layer neural network, you can use to transform your inputs from the input space into some larger or differently structured latent space H. Okay? But really, the interesting part of how transformers operate is when you allow them to interchange information across different tokens. So specifically, what happens here is you are going to update how you understand each of these tokens by computing a weighted combination across all of the other tokens. So in this case, you can compute the updated representation of the token off by summing up across all of the other words the embeddings of those particular tokens transformed by a value matrix V. And how much you value each one of these tokens, you scale using this Softmax function. So inside the Softmax function, what you compute is a query vector for the word you're looking at right now, that's off, and you take a dot product of that query vector with a key vector for your corresponding input token. And then the softmax function normalizes the numbers that come out of this dot product so that they sum up to 1. And you use those as coefficients for each one of the other words. So the key part here is that the representation of each token ends up transformed as a weighted sum of all of the value vectors of the tokens. And the weights in this weighted sum are computed based on dot products between queries for the token you care about and keys for the token you're attending over. This is also known as a self-attention mechanism. And then once this process repeats itself for a few layers, so you take some feed-forward networks, some attention networks, some feed-forward, some attention, when you're ready, you can then use these embeddings of tokens to predict the next token. So the first one can be trained to predict house, the second one can be trained to predict off, and the third one can be trained to predict cards. Now, one thing which is very important is what allows you to scalably train systems like these is the fact that you can take an entire sentence like this and immediately train on the next token for every single token in the sequence. So you're kind of simultaneously predicting both for A, both for house, both for off. And for this reason, to enable this scalable, immediate training on everything, this part here, the part which has the interactions between the tokens, you cannot allow every token to talk to every other token. So for example, the embedding of house cannot talk to the Z embedding of A, because then A would immediately know that the next word is house, and the task of classifying house would be trivial, right? So you really need to make sure that as you're doing this, no information leaks from the future into the past. And this is the reason why when I drew the arrows for the attention layer, I never had an arrow from off to A or from house to A. The arrows are only allowed to move forwards. And if you do things this way, this is called a causal mask. You've got yourself a modern decoder-only transformer, which is the essence of virtually all modern LLM assistants like Gemini, ChatGPT, Claude, and so on. Okay. So hopefully now we are all on the same page about how, at least on a high level, these models work. So now we can start to dissect why do they perform so badly on tasks like CLRS-Text. So the first card I'm going to present you with today is our transformers in glasses paper. And the reason why I've used the Joker to represent this card is because transformers are a little bit like the Joker. They always have tricks up their sleeves, so they're able to convince you of really incredible feats of reasoning. But unfortunately, they have somewhat poor eyesight, and it would be great if we could somehow give them glasses to sharpen their eyesight. And we'll explain what exactly we mean by the poor eyesight here. It basically relates to information getting lost as a result of having to focus on too many things. So allow me to just quickly take you back to the out-of-distribution result we saw. It's very weak, and it's not only very weak, it weakens almost immediately as you escape the largest size you've trained the transformer on, right? And this is interesting because graph neural networks, we talked before about our generalist graph neural network, that model had pretty decent performance on input graphs that were 4 times larger than what we trained the model on. Whereas you take a modern language model, and it doesn't seem to be able to generalize even to problems that have only 1 or 2 extra elements. So why is this discrepancy there? Why are graph neural networks performing so much better than large language models here? And we wanted to try to understand this better, and we tried to prompt these language models on much simpler tasks than what is in CLRS, tasks involving very simple copying operations. So, and we didn't even ask the model to copy everything we give it. We asked it to copy just one part of the input. And we asked it questions like, what is the last digit of a bit string like this, where you have a bunch of 1s followed by a 0? And also we asked, what is the first digit of a bit string of 0 followed by a bunch of 1s? Now, the first thing we notice is that after, as you increase the number of 1s in this question, the model will eventually start failing to answer such questions. And this holds for every language model we played with at the time. But one failure mode you might find very peculiar is that it fails on predicting the last digit. And this might feel very counterintuitive, right? You would expect the model to focus a lot of its attention on the things that are at the very end of your input, right? So basically, that 0 at the end is very fresh in the model's memory, and you would expect it will be able to retrieve it very quickly. And in fact, if you ask a human to predict the last digit of a long sequence, a human will be way more likely to predict correctly the last digit because that's the last thing they heard than the first digit, which might be long forgotten by the time they hear all of the other context. So this is very interesting and something we set out to study more. And we believe that the reason why this happens is precisely because of the way these models are trained, because they have this autoregressive nature of always predicting the next item, then conditioning everything on that prediction. Because all the paths that matter to predict the next part of your output must cross in that final token, right? So if we go back to our picture here, to predict the word cards, you really only need Z off. That's the only vector that is consequential for the prediction of cards. All the other Zs are not important. So you really, whatever information you need to predict cards, it must make it into Z off well on time for that to work. And because this final token is basically introducing an information bottleneck, like information from a potentially really huge sentence must flow into a single vector, this one vector is placed under a lot of pressure. And we use this pressure to first prove that you can always construct a family of inputs, which is a predictable family of inputs, like these bunch of 1s followed by a 0, that allow us to take the representation of that last token and pull it closer and closer and closer together across 2 different inputs. And we can prove that actually the representation of that final 0, as we increase the number of 1s, can get as close as you want it to. And of course, at some point, the difference between these 2 vectors can be less than machine epsilon, right? And hopefully you're familiar with the concept of machine epsilon and floating point data types. Basically, computers cannot represent every single real number. Computers can only represent a certain predefined set of rational numbers. And then as you get closer to these two numbers, and once you cross machine epsilon, like a computer must treat them basically the same way. And this is the reason why, as you add more ones, eventually you'll end up in a situation where you'll have two different inputs, which might need to be classified differently, mapped to the same vector. And at that point, the model will not have a chance to answer differently for those two inputs. And another thing which also explains why predicting the first digit was so much easier than predicting the last digit is relating to the very shape of the computational graph of the transformer. Remember, information cannot flow into the past the way these models are trained today. And what this means actually is there is a very strong bias imposed on tokens that are earlier in the sequence. And I've illustrated this just using the help of LaTeX. So I've picked this input sentence with 5 tokens, and I've taken an early token in blue and a late token in red, and I've covered every path from the late token into the bottleneck in a red color, and I've colored every path from the early token to the bottleneck in a blue color. And, I did not give it any further direction. Everything in this picture was just LaTeX mixing colors. As you can see, the color eventually turns completely blue. The early token has so many more paths, exponentially more paths to the bottleneck than the token at the end, that it will eventually just simply overwhelm it, right? There is a topological disadvantage given to token 2 compared to token 4. So it's not just that the information is squashed inside this final token, it's also squashed in an unfair manner. It gives a lot more favor to earlier tokens versus the latter tokens. And actually, when you combine this information with the fact that the English language and many other languages, the next token prediction task will often depend on the last few tokens in a sequence. So it might be totally expected that the model will learn or try really hard to counteract this effect by just attending very strongly to the latest elements and discarding the earlier ones in the coefficients. This is why you get when you ask a model to retrieve a needle in a haystack, like an important document in a sea of tokens. Typically, the performance profile will look U-shaped, like a U-curve. So it will be really good at predicting things at the beginning. It'll be really good at predicting things at the end. And then the things in the middle, the tokens in the middle, end up left behind as a consequence of this tug of war between the topological advantage given to earlier tokens and the bias of the English language biasing you towards the latter tokens. So as a result, because you have these unfair squashings of information, we can actually prove that frontier language models will struggle with even simple rudimentary counting and copying tasks. And it actually gets worse when you have repetitions, and adding chain of thought doesn't really help. And what you see in these plots, each column of these plots is a particular task which is relevant. So summing up a bunch of ones, 1 plus 1 plus 1 plus 1, counting ones in a bit string of ones, counting ones in a random bit string, and counting words in a sentence. These are some 4 specific copying and counting tasks that you might find interesting. The blue bars are the errors that the model makes. So the bigger the blue bar, the bigger the error that the model makes. And the x-axis here are problem sizes. How many digits are you counting? How many words are you counting? And you can see that all of these lines tend to shoot up as you increase the problem size. Although you might also notice that the blue lines are kind of growing in a relatively predictable manner. So you might still wonder, okay, could it be that the model is just like approximately trying to fit the problem, but the approximation gets worse over time? To be honest, I would be happy if that was the case, because I think that humans are also capable of reasoning. kind of by definition. And we humans often use approximate reasoning to arrive at the conclusions that we want, right? So even if it was an approximation, if it was a sort of a kind of well-defined approximation, then this would be fine. However, then you plot the distribution of the answers the model gives across all of these different tasks, and you immediately see that it doesn't really even approximately understand what it's doing. Rather, here you see the distribution across all possible output values. You would expect the true answer to be roughly balanced across different numbers. However, the language model really, really likes the number 100. Okay? So this to me says, and it's very evident, the frontier models are not really learning to count or trying to count at all, or even trying to follow an imperfect algorithm. They're just seeing, oh, there's a bunch of ones in here. Let me guess that there is 100 of them, because 100 is a nice round number, and it's sort of, it feels like that kind of scale, right? So I hope this can give you very concrete evidence that this kind of knowledge, like rigorously understanding how to do even simple things like counting and copying, isn't something that these models are able to do. And counting and copying are really foundational operations. You cannot do many important autonomous tasks without first knowing how to do this. And one other important point to note is that these errors happen way earlier than the theorems we predict they would, okay? And we think that this is because, like we talked about, bringing two inputs closer together until they're below machine epsilon close together. This is because in modern language models, especially the ones you interact with online, very often machine epsilon is blown up. Okay, it's much bigger than what you would expect, like in a 32-bit precision floating point number. And that's likely because, first of all, these models are already trained using low precision types, like 16-bit floating points. But then when they're served to you, when you perform inference in real time, they're often further quantized. So this means that you additionally chop up the bits used to represent a number so that the actual smallest difference that these numbers can represent grows and grows. And very soon the machine epsilon becomes way bigger than what you initially bargained for. Now, you might say that these kinds of problems like copying and counting can be easily solved by using tools like asking the model to write code and then running the code. But I'll just say, especially if you want the model to work on something without heavy human supervision, good luck using a tool if you can't even copy some input in and out of it. I've actually noticed frontier models fail very spectacularly in this way. When you ask it to solve a challenging problem, it actually writes the code. The code is completely accurate. It copies the input into this code properly. The code predicts the correct answer. And then the model takes that output of the code and fails to copy it at the end. So basically, it's done everything right, but it's failed to copy the output properly when it's served to the user. And at this point, a user might be able to manually notice this and correct. But if you want a system that like autonomously executes a sequence of tasks, this silly mistake, basically. Okay. And once again, the important thing to remember is the reason why we showed that there is this bottleneck, this large amount of pressure on the final token, is because we're using these causal masks. So we're only allowing a token to send its information into the future, never into the past. It allows us really to train at scale, but it also exposes the model to this last token bottleneck, which can be fatal depending on the task you want it to do. This is as far as I'm going to talk about this particular card. If you would like to know more about it, we archive and we had published it at NeurIPS a couple of months ago. So if you want to know more about our theorems, our assumptions, how does this apply to language models, as well as some interesting ways in which you might fix the problem, please take a look at our paper for more information. But for us, it is time to move on to card number 2. So we've talked about a very drastic problem. Now let's try to think a little bit about how we might, at least aspirationally, be able to solve that problem. And we are going to study the augmentation of transformers with neural algorithmic reasoners, or NARs. And for NARs, we have decided to use the jack. And the reason why I'm using the jack is when you combine the transformer with the neural algorithmic reasoner, the transformer will acquire a jack of all reasoning traits. And it will sort of be able to ameliorate some of these issues that we previously said they cannot work their way around. So ideally, since we know that the causal masks are a root cause of the problem, ideally, we would just be able to fix this problem by allowing the model to unrestrictedly allow different tokens to talk to each other. This was actually done by the original transformer paper, and for many years was a gold standard in natural language processing. You might have heard about the BERT model. Before the rise of modern large language models, BERT was the industry standard, and it was basically a transformer where all pairs of tokens could talk to each other. And it was trained in a very different way to modern next token predictors. However, as we just discussed, even though you could, in theory, allow all the tokens to talk to each other, you would then not be able to train on an entire sentence at once, because you would be cheating for predicting all of the previous steps. So this is harmful to scale. So in our work, we actually tried to ask a slightly different question. What if instead we could train a graph neural network, which we know generalizes quite well from the results I showed you before? What if we train that on graph-related tasks and then ask a language model to leverage that knowledge, right? In a sort of multimodal fashion, right? So we have graphs on one side, we have text on another, and we've trained the graph model to work on graphs in a non-autoregressive fashion, and we allow the language model to take that knowledge for itself. This idea leads us to what became known as the trans-NAR architecture, the transformer neural algorithmic reasoning architecture. On a high level, it's a relatively simple idea. You have your language model taking tokens as input and producing tokens as output, as you would expect. But then at the bottom, you also have a graph representation of your problem. And then that goes through a graph neural network, as we discussed before, our neural algorithmic reasoner, or NAR. And what happens is you allow this language model to periodically talk to the graph model and exchange information. This is really the core idea. Through interacting with this graph model, which doesn't have the limitations of causal masks, the language model might be able to gain access to information that it otherwise wouldn't have been able to access very easily. When you zoom into this equationally, this is typically what it looks like. So you feed to this model a sequence of tokens, that's your text, and a graph structure, that's your graph input. You pass the tokens through the transformer, as we discussed before. You pass your graph model through a graph neural network, as we briefly discussed in the generalist model from log. And once you have the embeddings of the graphs nodes and the embeddings of the text tokens, you can just allow the nodes to text through a cross-attention operation. So what over the nodes of the graph, equation like this, it was already well understood and explained in the Flamingo paper, Flamingo was one of the original vision language models. And it combined, in that case, data from text with data from an image. And this is now what a single block of trans-NAR looks like. And it performs really, really well compared to the baseline transformers. So here in red, you see the CLRS-Text on various tasks. So here grouped into several like string matching, really tasks, just make a plot a bit easier to read. And in red, you see the performance. The y-axis here is once again from 0 to 1, so big. In fact, they are often level of 20.
এ বাবা টক থেকে বেরিয়ে গেল তো নেটওয়ার্ক ইস্যু
Okay, we should be back now.
yeah sure you can continue from there.
Right. Yeah. Apologies about this. I hope that not too many slides were left uncovered by this network issue.
Only this slide, yes, this slide. You can discuss this slide
Okay.
once, please.
Sure. Yeah, sorry about that. My internet is quite flaky, and this might happen a few more times, but please bear with me. We'll manage. I have 3 different sources of internet. We'll make it work. Okay, so going back to the transnar model, just once again, and updates their representations in the same way we discussed before. We have a graph neural network algorithmic reasoner, which takes the nodes of the graph and updates them in a high-dimensional space, much like we've covered in the when we briefly mentioned the generalist paper from Ibarz and others that was published at Log, where we had 1 GNN trained to execute 30 algorithms. And then once we have these token embeddings and these graph node embeddings, we can basically allow information from one of them to influence another through a so-called cross-attention operation. What this means is that each of these tokens attends over all of the nodes in the graph, and that way gaining access to the knowledge that's contained inside the graph's nodes. And we are not the first paper to propose this kind of operation. In fact, Flamingo, one of the earliest vision language models, has done exactly the same thing in combining information from text and images. So this was a well-established formula by the time we proposed transnar. And immediately, this architecture unlocks basically a wealth of knowledge. And specifically, it is outperforming a baseline transformer on a lot of these algorithmic tasks in CLRS-Text pretty much out of the box. So the red bars here are the performance of a baseline transformer on different algorithmic classes like dynamic programming, graph algorithms, greedy algorithms, sorting algorithms, and so on. And once again, the y-axis here is from 0 to 1, which means that many of these gaps are huge, like 40% or 60%. In fact, there are even some problems where the baseline transformer has 0% accuracy, so it's not really learning anything. And the transnar variant is able to get up to 40 or 60%, which means there's a new emerging skill that has come out by allowing the transformer to use this knowledge. So this is basically an architecture, first prototype of such an architecture that we were quite happy with, and we presented it at the CVPR MAR workshop, and the work is public on the archive, so you can feel free to check it out if you want to know more. Before I move on to the next card, I would like to quickly remark some more broader thoughts on transnar. So I think it illustrates why multimodality might be a good thing to embrace when you're solving reasoning tasks. And basically, the graph solves the problem of data only being able to flow in one direction, because the graph doesn't have that restriction. You can have data flowing wherever you want. However, as I'm sure many of you have noticed, this model cannot be very easily practically useful, because I cannot run it if you don't give me a graph structured input, right? So if my problem only has text and not graphs, I won't be able to run TransNAR out of the box on a task like this. But we do hope that our result motivates that there's plethora of hidden knowledge hidden inside these graphs. And therefore, basically, that there might be other ways to exploit that knowledge and reach really improved levels of reasoning. And one particular avenue that we decided to explore towards this, it might not be the only way, is the avenue of distillation. So we could take a trained TransNAR model and use its knowledge to train a basic transformer, a student model, which imitates whatever predictions and distributions the TransNAR model has. And we already have some pretty promising results. So here is a collection of 8 different algorithms from CLRS-Text and the out-of-distribution performance. The red bar here is the baseline transformer, which doesn't have any graph input and has only been trained using next token prediction. And in the different colored plots, you have that same transformer, but trained using some combination of next token prediction and imitation of TransNAR. So you can see, obviously, performance metrics are different for different tasks and different choices of how much you value TransNAR prediction versus next token prediction. But you can see that a lot of these bars are significantly better than the baseline transformer. So even through a simple process of distillation, you can take the knowledge contained inside such a TransNAR model and bestow it upon a unimodal transformer, which then you can use on a bunch of other problems. So this already hints at one way in which we can take these gains and at least transfer some of them into modern transformers. And what's great is that these benefits transfer even beyond the original out-of-distribution sizes into problems that are even larger. So this plots here is looking at larger as well as smaller problem sizes than what we've seen at training time. Okay, so now I'm going to switch gears a little bit. We talked about the computation graph of the transformer, and we talked about ways in which we might be able to fix it by introducing components which just on the side leverage a full connectivity pattern. Now we're going to talk a little bit more about the operation that takes place over this graph, specifically the softmax function. And for this card, I have taken the 10 of hearts. It is the card which has the most hearts on it, and therefore the most energy. And just like the 10 of hearts, it's a really high dose of energy. And at some point, this energy proves too much for the poor softmax function to contain. And that is exactly the effect we explored in this paper. So I trust many of you or all of you are already well familiar with the softmax function. It's used as a standard function in classification objectives, and it's also used as a central function inside attention mechanisms. Its main purpose is to take a vector of numbers and transform it to get probabilities. So to get normalized numbers that sum up to 1. So you take a list of these numbers, which we call logits, E1, E2, all the way to En for n items or n tokens. And you normalize them. You first take the exponential of each, and then you normalize that. This way, you will obtain your values that sum up to 1 in a way that can be related to the Boltzmann distribution. Besides the logits, you also have access to a temperature hyperparameter, theta, and it basically controls how much importance should the model give to the highest logit item. As the temperature value approaches 0, all of these values will go to infinity. but the value of the highest item, the argmax item, will approach infinity faster than everybody else. So basically, as temperature goes to 0, you'll end up with a sharp one-hot distribution where the model only attends over the argmax item. And as temperature goes towards infinity, the contribution of each item becomes negligible, and you basically end up with a uniform distribution. Okay. This is a trend that permeates transformer research ever since the original transformer paper. This I've shown you on this slide a picture from the original vanilla transformer paper, Attention is All You Need, that was published at NeurIPS 2017. It's generally understood that the way in which these models learn to perform tasks so well is because they learn what we call sharp behaviors. So even though you have a sea of possible tokens sending information to a particular target token, that token can use Softmax to focus on a very small proportion of them, and then the coefficients for the others will be negligible. So here you see an example from the original transformer paper concerning a translation task from English to French, and you can see how a word will tend to focus its attention over words that are sententially most relevant to that particular word. Okay. However, the key thing that we show in our paper, the key thing that we prove in our paper, is that this effect cannot persist. So any sort of sharpness you observe when you feed inputs that the Softmax, the transformer, is familiar with, that sharpness cannot persist. So what we mean is, here you have your typical transformer architecture, and let's say that on some input size that the model has seen during training, so it's in distribution, you'll end up with attention coefficients that support sharp behavior. So here, say, token 4 gets a really sharp coefficient close to 1, and the model is like really zoning in on that one. We can prove that as you increase the number of items, and it really doesn't matter what these items are. They can be complete garbage, complete noise. They don't have to be anything like really distracting. It's provable that eventually the sharpness will fade, and this item 4, which used to be really sharp, will now have a very comparatively low probability. And actually, we can force that probability to go as low as we want it to. Any epsilon bigger than 0 is fair game. Now, what's important is that this is not just a theoretical effect that will sort of happen, but we never really see it. You can observe these effects in attentional models of various shapes and sizes. So let's just start with a very simple task: find the maximum in a list of items. I deliberately choose the maximum because the softmax function is sort of designed to approximate the maximum in a more differentiable, gradient-friendly way. So let's start with a simple single head set transformer architecture. So this model only has a single attention head. What's very nice about it is that we can directly correlate what that attention head is learning to do with the final predictive power, because it's kind of causally related. Either that one head has learned how to extract the maximum, or the model will struggle, right? So what I show you in this visualization is a visualization of the attention coefficients on the 16 largest items for a randomly sampled collection of input number sets. So every single row in this picture is one particular randomly generated input, and the 16 columns are the attention coefficients on the 16 biggest items. Every single frame of this animation, I doubled the number of items in the sequence. So you would expect a good max predictor to focus all of its attention on the far right. So you'd expect a big dark column on the far right, and that indeed is the case for smaller sizes. But see how as I increase the size, the coefficient on the largest item disperses and eventually completely disappears. It basically becomes a uniform distribution at that point. So this is an effect we can very nicely observe and correlate with downstream performance as we increase the problem size at test time. But you can also observe this in modern large-scale language models. Now, here we have the 2 billion parameter Gemma model, which is open and anybody can play with it. So basically, of course, in the case of large language models, there's so many different attention heads, and you cannot nicely correlate what one head is doing with the final performance. But plot how one very nice proxy for sharpness is the entropy measure. The larger the entropy, the more chaotic the system, the less sharp it is. And you can see as we increase the number of items fed into a language model, the entropy values tend to shoot up. And the heads become less and less sharp. And this is just an effect we observe. As I said, we have been able to prove a theorem. This is a direct quote of the theorem from our paper. I will not dive into the specifics of this theorem in this talk, but what I will tell you about is which parts of this theorem, which are the key assumptions of this theorem, okay? That this proof relies on, and actually, hopefully, you will agree that these assumptions are not particularly unrealistic. So the first assumption is that we have non-zero temperature. This should be fairly obvious because if temperature is 0, then you have sharpness to the argmax, and the model will never disperse, right? As we assume non-zero temperature, we assume that our inputs come from a fixed vocabulary of tokens. This is definitely the case of modern language models. We still rely heavily on tokenization. We have attention heads fully attending over tokens. This is also for most attention heads in modern transformers.
Peter, there is some problem in changing the slides.
Max self-attention
Peter?
or continuous feed.
Your voice is breaking and the slides are not advancing.
As discussed when we
Peter, can you hear us?
transformer architecture before.
Peter, can you hear us?
I hope you'll agree with the assumptions are not unrealistic, and certainly represent many of the modern large language models in circulation. I specifically want to focus for a little bit on the first assumption, so temperature bigger. Could we just fix this problem by setting certain tension temperature to 0? Well, not so fast. We actually have another proposition. Okay. Yes.
Hello.
I can hear you. Can you hear me?
Yeah.
Yeah.
Your slides are not advancing, actually. We are still an earlier slide. I think there is a network issue. Your slides are not visible.
Can you hear me? Maybe let's start from that.
Yeah. Now we can hear you. Now we can hear you from this slide, maybe.
Okay. So what slide are we on now? Like, what slide can you see? Maybe that's a good question.
Which assumptions can you break? Which assumptions can you break? The theory relies on a few assumptions.
3.1.
Yeah. Okay. So I haven't really advanced beyond this point. So
yeah, it just came in right now.
Okay. Fair enough. So what's the last slide where you were able to see? Did you see this one before?
No, not this one.
No.
Oh,
you can
okay.
One step back. Yeah, this is where we were.
Okay. Sorry, internet source number 3. Maybe this one will work a little bit better. Okay. So, right. So hopefully I don't have to convince you again that softmax coefficients will totally disperse as you increase the problem size. And this is true empirically as well as theoretically. So we have been able to prove this. And this particular theorem is from our paper, and it basically proves that this effect of we can make the coefficients as small as you want them to be. This must happen in modern language models the way they are constructed. Now, I don't have time, and I'm not intending to dive into how this theorem works in this talk. You can obviously read the paper later if you want to know more about it. What I want to focus on is what are the assumptions of that theorem, okay? So first of all, so you can agree with me that hopefully those assumptions are not too strong. And secondly, so that we can collectively discuss which of those assumptions we might break the most easily to hopefully build a model which doesn't suffer from this problem. So there's 4 main assumptions in the theorem. The first one is that temperature is non-zero. This should hopefully be relatively obvious, because if the temperature was 0, then there will be no dispersion ever, because all heads would just attend to the argmax. So, and hopefully it's understandable why this is sensible. You often want to be able to attend over multiple things, and as a result, temperature in most modern LLMs is never set to 0. Second, we assume our inputs must come from a fixed tokenized vocabulary. So basically, you assume your input can be cut up into these tokens, and these tokens must come from a predefined vocabulary. This is, once again, a pretty standard assumption. All modern LLMs do this. They're all tokenized. The third part is that every one of the attention heads you care about will attend over all previous tokens. There is some research in local attention recently which breaks this assumption, but every single popular frontier LLM that I'm aware of has at least some heads which rely on attending over all the items. So this assumption is also very much not unrealistic. And the last assumption is that all the layers are either feed-forward networks or softmax self-attention, which are, you can think of this as a standard assumption, which is how modern language models are built. So all 4 of these, I hope you'll agree with me, are fair assumptions. No other assumptions are given. And maybe the first one that sticks out, the one that I want to focus on for a little bit more, is this idea of temperature bigger than 0. Could we fix the problem by just setting the temperature in a few places to 0? Well, not so fast. Unfortunately, in our work, we have been able to prove that this might be a really dangerous operation to do. And the reason why is because to get sharpness in the first place, so to get into a situation where on the training examples that you have seen at training time, you get sharp coefficients, you really need to, the only way in which you can achieve that is by increasing your weight magnitudes. So what does this mean? This means that you can never split your different token logits more than this upper bound given at the bottom of the slide, which depends directly on the largest singular values of your parameter matrices. So the only way in which you can get sharp predictions in a transformer is by having larger and larger norms of your weights. And as we know, the larger your norm, the more likely it is you're going to overfit to your data. And the more likely it is that the item with the largest logit is not the item you actually care about. And as a result, we decided to try to explore a sort of middle ground where, okay, clearly decreasing the temperature might be a good idea, but setting it to 0 might be too bad. So let's try to learn a more adaptive function, which will decrease the temperature adaptively depending on how sharp the head was to begin with. And we can use, as I said before, entropy as the proxy of this. So we've gathered a bunch of empirical data of input sets where the item we care about the most didn't receive the largest logit. And we checked what is the optimal temperature. For those kinds of inputs, there is the optimal temperature level at which the item we care about will receive the highest logit possible. Beyond that, the logit will decay again. And we tried to fit an inverse polynomial function to this data that we observed. So here the x-axis is the entropy of the head. The y-axis is the optimal temperature value. And we then take this polynomial and modify our original softmax to adjust the temperature based on the entropy. So what we do in our experiments is whenever you see a softmax in the architecture, you replace it with this block of Jack's code, which adaptively multiplies the logits depending on the entropy. That's really the main purpose of this. And it turns out when you do this, even on our single attention head, out of the box, without any additional training, so you're taking a model that was pre-trained without adaptive temperature, and then you're applying adaptive temperature to that head, you immediately start to see benefits on out-of-distribution sizes, and these benefits are statistically significant. You can see the p-values from a paired t-test at the bottom. And you can also notice just the improved sharpness of the attention head before and after. So before is at the top and after is at the bottom. You can see how, especially as the sizes increase, the original attention head will start to fade, whereas the temperature corrected one will remain sharp for longer and the coefficients will be generally more lit. And also notice why we cannot set temperature to 0. Because in a lot of these cases, especially as you increase the size, the most important item, the one on the far right, just doesn't have the largest coefficient. You cannot save yourself by setting temperature to 0 here. What's cool is that you can then also apply this new softmax in a large language model. So you can try to take every single attention head in Gemma 2B, which is a 2 billion parameter model, and set its softmax to adaptively multiply based on the entropy. The main difference is, compared to this experiment, is that now the model is a complex combination of many heads, and not all of them actually need to be sharp for the prediction to work. So you cannot just blindly apply this to every single head without retraining the model. So we find that in this case, you actually do need to fine-tune the model a bit more. But once you do that, you get immediate benefits on the CLRS-Text tasks. So here the blue and red models are identical Gemma models, but one of them was tuned without the entropy correction, and the other one was tuned with the entropy correction. You can immediately see the benefits in the predictive accuracy at various sizes, and sometimes these benefits are drastic, 40 to 60%. So, okay, this was our discussion of adapting the temperature. And we said you cannot really set the temperature to 0. That won't work the way the models are built today. And also, adapting the temperature is a nice kind of ad hoc patch, but it's not really something that will fix the problem. Like, the problem is still going to be there even if you multiply the weights. So I actually think we need to focus a bit more in the other 3 assumptions and see what we can do there. So as a consequence, I'm really interested in developments that lead to token-free large language models, more sparse attentional mechanisms, alternatives to softmax, which will cause sparsity to kind of natively emerge, or even, and I've studied this with a few co-authors a few years ago, having feed-forward networks that are discontinuous. So our proof relies on all the functions of interest being continuous. But if you introduce discontinuities at very specific points, such that gradients could still flow meaningfully, but the model actually no longer satisfies continuity, you wouldn't have this issue to deal with. So I'm really excited about all 4 of these directions. We hope to contribute to some of them over the coming months. But those are really what I think will solve the problem of dispersing coefficients. We have released this work as well. It's available on the archive. It was published at a NeurIPS workshop a couple of months back. It actually also won a Best Paper Runner-Up award there. So all the information are available if you want to read more about this phenomenon. I do think that it's going to be a really important issue to address as we develop attentional mechanisms of the future. Okay. Moving on to card number 4. Here, we are going to talk about position embeddings, and we're going to talk about rotation. So far, we've talked a lot about the shape of the attention mechanism and the computations of the attention mechanism. Now we're going to switch gears and talk about the position embeddings. And I've decided to choose the 2 of clubs for this particular card because you have this really rapid rotation of the club from 0 degrees to 180 degrees. And it's rotating so fast, all the other symbols that rotate slower are left behind. And this, I think, nicely illustrates the message of what this paper will be all about. So if you remember, when I was showing you those performance numbers for CLRS-Text, we showed that there can be a big difference depending on how you choose to set up your position embeddings. So those are clearly important. Let's talk more about them now. So specifically, position embeddings are an additional piece of information telling the model for each token where is it in the sentence. Position 0, position 1, position 2. This helps the model, for example, to establish some causal relationships. If not appears before a word, it's not the same than if the not appears after the word. So you cannot just take bags of words and expect good performance. You really need to take into account the positions of the words. And when it comes to positioning, most modern LLMs that I'm aware of use rotary position embeddings, or ROPE for short, to orient themselves. The way it works is they partition the embedding space into 2-dimensional blocks. So where D is our embedding space, so the size of our vectors, you take 2-dimensional chunks. There's D divided by 2, many of them. And for each chunk, you have a different rate of rotation. This theta raised to a particular power. And then what you do is you compute a rotation matrix based on that particular rate of rotation. That's the rho of GK. And what you do when you compute a rope dot product, as opposed to a usual dot product, is before you take a dot product of the query vector with the key vector, you also apply an appropriate rotation, which depends on the difference, on the distance between the 2 points. And this really just means adding an extra rotational factor where the rate of rotation depends on both the chosen subcomponent of the embedding, so this K, and also the distance, which is the power you raise this matrix on, so how many rotations you will do. And one thing that's generally understood about rope, or at least this is a quote from its original paper which proposed it, is that the reason why it works so well is because as you increase the distance between the 2 nodes, there is a gradual decay of the resulting dot product, and this allows the model to more sharply focus locally on what's happening and therefore be less distracted by things that are far away. We actually proved that this is completely not true. So we dispel the entire myth about rope being about decaying activations. Well, okay, first of all, we reproduced the results from the original paper, which used constant query and key vectors, which you'll agree with me is a very specific regime, which doesn't necessarily correspond to reality. But sure, in the regime where all the query and key vectors are the same, as you increase the distance between tokens, the rope coefficients drop and they decay quite predictably. However, what if instead we choose to use randomly sampled Gaussians as our queries and keys? Actually, what happens is no more decay can be observed, and it's completely noisy, right? So relating to this finding, we first proved that you can actually maximize the rope coefficient at an arbitrary distance. It doesn't decay with distance. So for any query and a particular distance I want to maximize, there will always exist a key such that the softmax will peak at that distance. And secondly, for the case of Gaussians, the expected value of this dot product between query and key is 0 in a way that doesn't depend on distance at all. So for Gaussians, it's the extreme case because there's 0 dependence on how far away the 2 tokens are, and we can prove this. So, okay, since we've shown that you don't get this nice effect that the original paper was talking about, at least you don't get it in many situations that are important, how does rope then actually work? Well, we set out to kind of directly analyze a lot of different mechanisms inside modern large-scale transformers, and our analysis led us to this conclusion. The way in which you can orient yourself in a transformer is you've set your query vectors and key vectors to be constant, but you make the query vectors appropriately rotated to match a particular rotation of rope. Okay? And here I can use 2D vectors because rope does cut its vectors into 2-dimensional chunks. And then once you've done this, depending on how you've chosen your rotation, the query vector you care about will align itself with the appropriately rotated key vector of the target you're trying to hit, in this case, off by 1. And at that point, because the rope rotates really fast after that point, and because the rotation increments are rational numbers, and the surface of the surface of the circle is irrational, 2 pi, you can prove by using Dirichlet's principle, the pigeonhole principle, that actually no other vector other than this key vector will align itself perfectly with the query. And then at that point, you know that will have the largest coefficient, and you can just amplify the norm to increase that dot product and diminish all the other ones. And as a result, you obtain really sharp positional attention. So this is actually how rope is able to sharply attend to certain positions. In this case, it's off by 1 diagonal. So in this case, you've rotated your query vectors by 1 unit of rotation, and this basically lines up the key vector, which is 1 step behind, to give you this nice sharp off by 1 diagonal attention. And you can observe this empirically. So here is a purely diagonal head in Gemma 7b. And you can see it's purely diagonal, so all tokens just basically attend over themselves. And if you look at which parts of the rope spectrum are most used by norm, the high frequencies are most used. You have the darkest colors in the high frequencies. Otherwise, when you go outside of the realm of positional heads, so heads that like attend only over a certain position, high frequencies are actually quite rarely used. So we can very nicely correlate the heads which have high frequency with the fact that they will learn some off-diagonal behavior, like a positional behavior. And in comparison, most other heads tend to use the low frequencies. You can see most of the mass is concentrated in the low frequencies. And this is quite interesting, because these lowest frequencies, especially in modern language models, they actually have such a slow rate of rotation. So the theta is really, really small. So you're unlikely to actually have notable effects at those frequencies. So our guess is that the model uses those frequencies for semantic transfer of information. So this really is, the rotations are used at high frequency to help you attend on sharp positions. But on low frequencies, you actually mostly want to not spin very fast to avoid interference. However, these slow rotations still spin, and we can actually prove, at least for certain special case settings, that this will still cause interference and out of distribution make it really hard to propagate information meaningfully. And this then leads us to a very simple experiment. What if we just remove some of the lowest frequencies of rope? So we still keep the high frequencies. We know those are useful for positional attention. But for the low frequencies, we just set those to 0. And we make this, we call this approach p-rope. P-rope tells you, let's say 0.25 rope means you're retaining 25% of the frequencies, and all the other ones are set to 0. And we really get a pretty wild result when we do this out of the box on several general purpose language training corpora. Even if you delete 25% of the lowest frequencies, so this is the 0.75 rope result, you actually already get equal or better perplexity than full models using rope or no positional embeddings. And this is pretty cool. I mean, it's already pretty cool that I can delete a quarter of the rotational power of rope in modern architectures, and the performance doesn't get worse. But it even actually gets slightly better if you look at perplexities. So because this is perplexity, which is related to the log loss, lower is better. And it's pretty interesting, right? We actually recently got the exciting news that our paper was published at iClear. So for those of you who are traveling to Singapore later this year to listen to and watch the iClear presentations, our paper will be presented there. So you'll have a chance to talk to us. In the meantime, the paper is also public on the archive, so please feel free to check it out. Round and Round We Go is the title of the paper if you'd like to learn more. And the final card I would like to present to you today is sort of taking this idea of discovered positional attention and sort of doubling down on it and really trying to force the model into these behaviors. So I've chosen the 8 of diamonds because the diamond is a very sharp object, and these 8 diamonds are arranged in a very intricate pattern, and they're really holding their ground. They're remaining sharp as ever. So because we get sharpest attention when the model acts positionally, and we've seen from the Softmax paper that sharpness is a good thing, especially for reasoning, could we try to completely decouple position from state? So in this case, our attention only looks at position embeddings. It doesn't look at values anymore. So the actual things that are inside the tokens do not contribute to how the attention will go. They only go inside the feed-forward networks and the linear layers, but the model itself, when it decides where to send information, only uses position to conclude that. Now, this might sound like a crackpot idea at first, like completely crazy. But actually, there are some really good reasons why you might want to do this. If you don't depend on the value, so if your attention only depends on position, this means you can feed all sorts of crazy things on those same positions, and it will not affect the behavior of the system. It will not collapse as you give it wildly different values. So that's one thing that's good. Secondly, it actually doesn't limit the space of functions you can express because it relates to many well-known protocols in routing theory. And we have detailed proofs of this in the paper that I will share at the end. But basically, even if you only have a positional way of routing information, this relates to a well-known computational model in computer science, which is Turing complete. So it can represent any function that you want given the right amount of resources. And the main thing is that it actually also clearly decouples the roles of attention versus feed-forward networks. The attention heads are now routers. They just decide where will the information go, and the feed-forward networks are the processors. They will then take the information routed to them and make decisions, right? And you can sort of immediately see benefits from doing this. So first, we can look at out-of-distribution performance on various tasks like summing, taking minima, medians, sorting, or even solving an algorithm like maximum subarrays. Here, the y-axis is loss, so you want the values to be lower. Positional attention completely outperforms standard attention, and that's the only change we've made to this architecture, and it's a pretty sizable change in out-of-distribution loss. So this is one thing, and these are variable lengths. So we have the x-axis here is different range of values over which you're performing the computation. Another thing that's pretty interesting is that you get better generalization when you do this as you scale training examples. So one important point to note here is that value generalization is generally quite hard, and it's not something that magically gets better as you add more training examples. So as you can see here, the red is your usual attention, and the x-axis is the number of training samples. The out-of-distribution loss actually doesn't improve at all as you increase the training set. Whereas with the positional attention, not only does the loss start off much better than the normal attention, it also gets predictably better as you increase the number of training examples. So this is another pretty cool reason why positional attention might be a good idea. And also, we get a better level of size generalization, so generalization to bigger sizes that we discussed before. Here, unfortunately, even with positional attention, you'll get new positions at test times, so there will be some level of distribution shift, and the model performance will get slightly worse. But once again, even as the performance gets worse, the positional attention handles this much more gracefully than the standard attention. Of course, these are only preliminary experiments on carefully curated problems that are really designed to show off why the positional decoupling is a good idea. But we thought, since the models are already discovering positional attention by themselves through gradient descent and cleverly using rope, we were wondering, could it work to just fully make them positional? And this paper gives you first evidences that that is the case. The paper is public on the archive. You can look up positional attention and check it out if you want to know more. So that was my last slide. Thank you very much for bearing with me through several internet collapses and 5 different cards. I hope I've been able to teach you something interesting today about both the transformer architecture, how it generalizes out of distribution, or well, how it fails to generalize out of distribution, and maybe also what are some of the things we can do to make the situation a little bit better. Thank you so much, and I'm happy to take any questions you might have. Thanks again for kindly inviting me.
Thanks a lot, Peter, for this wonderful and insightful lecture. Now, may I request the participants, if you have any question, you can either type on your chat or just simply unmute yourself and ask.
So I have one question. So it is on the last slide for positional attention. There are some tasks you have shown loss improvement plots, some minimum and median. So how you are creating this OOD data, out of distribution data, to test the models?
So there are several out of distribution shifts tested here. In plots like these, it's value scale. So the x-axis here is scale. So the number of items is kept fixed, but the scale of each item is changed. So if you imagine it's like sampling each number from a uniform distribution, you change the bounds of the uniform distribution. So this is one out of distribution regime. Another, well, this is not really, this is that same out of distribution regime, but checking does it get better as you include more training data. So it does get better in the positional, but not in the standard. And this one is the more usual size generalization we talked about before, where you train on smaller numbers of items and test on larger numbers of items. So those are the main types of out of distribution we tested here.
Okay, thank you so much. So I have one more question. So it is related to transformer NAR. So can we use that on our personal computer, or it is a huge model? Like, can we use it?
Right. So, well, the trans part of TransNAR, so the transformer, is as large as you want it to be.
Yes.
We have, we have observed benefits even with very small scale transformers, and usually for these algorithmic tasks, you don't need really huge transformers to get the point across. Like, these tasks are severely overparametrized, so even the smallest GPT-2 model, for example, is already kind of equally powerful when you fine-tune it as, say, a large-scale Gemma model. So that's one thing. The NAR part is even smaller than that. So the GNN is kind of really small and really targeted and knows how to do these tasks really well. So typically the scale of parameters in those models is on the order of hundreds of thousands. So an order of magnitude less than even the smallest transformers. So yeah, this is a model you can totally build and deploy on your computer. The scale that you'll be able to run is actually governed by which transformer you choose to use. But the NAR part doesn't add extra prohibitive cost to the scale.
Okay. Sir, I have one more. So it is yeah. So in this lecture, overall, we have discussed basically the limitations of transformer, like it suffer OOD, generalization, and over squashing. But the same problems happen with the general GNNs also. Graph neural network also suffer out of distribution data when it comes to, and over squashing also one issue is there in GNNs. So what is your call on that?
Okay, so that's a great point. I will quickly say every neural network model suffers out of distribution. Yes. But as we mentioned when we talked about the first card, GNNs suffer when you amplify the problem size by a factor of 4. Transformers suffer when you add 1 item. So clearly there is a huge discrepancy in when failures start to occur with GNNs versus transformers. So there's certainly something that the GNN knows that the transformer does not, right? So there is a much different gap in when the failures start to happen. But they will always happen. Like, out of distribution generalization is not a solved problem. GNNs don't solve it, but they're certainly much better at it. So that's the first thing. And the second thing about the over-squashing. So this is a very interesting point. Over-squashing is a function of the computational graph structure you use, okay? And we've shown specifically that the fully connected causal graph, which transformers use, is a really bad structure for over-squashing. So when you use a more generic unrestricted GNN, you can use a graph for which you know over-squashing is less likely to happen. Specifically, in all the NARs, we use the fully connected graph, which we know is much less vulnerable to these effects.
Okay, thank you so much, sir.
No worries. Thanks for asking. These were great questions.
Any other question? Yes, Devanjan has a question on the chat. Peter, can you see that? Given the challenges from us face?
Yes, I can see it. Maybe I'll just read it out so that it's properly captured and everybody can hear. So, given the challenges transformers face, issues with length generalization, and we've seen improvisation with chain of thought, are there similar studies with in-context learning? Basically, yes, and I think I've shown this plot. Let me get back to it. It's happened a fair few slides ago when I first presented CLRS-Text here, right? So the green curve here is in-context learning, yeah? So that's much, much worse than training. This is what I meant when I said a benefit of fine-tuning. Like, there is some knowledge inside these examples that you clearly could learn in a transformer. That's why the blue and the orange curves are doing so much better. But pure in-context learning on a big model just doesn't work. Like, it doesn't work as well as you want it to. And this is this specific plot is two-shot learning. So we give the model 2 examples, and then we ask it to solve a third one. So I hope this answers your question.
Any other question from any other participant, please?
Hello, Peter. I would like to ask something. Like few slides back, you were discussing about the decrement of the blowing up of the machine epsilon. So, as to the best of my understanding, I understand that this caused by training and testing on low precision floating points. So, is there any other reasons that are causing this machine epsilon to blow up?
Yeah, so basically, I mean, what the machine epsilon will be is a function of the number type that you use, right? So as we said, computers cannot represent every real number. They can only represent a subset, and which subset they represent depends on the type you use. So do you use float 32, float 16, float 8, B float 16, or even quantization, where actually I don't think it's floating point anymore. It becomes fixed point at that point. So it's really, it's an inherent function of the number type you choose to use to represent your numbers, and it's not governed by anything else. So it's really the numerics of the type. Of course, maybe at some point in the future you could have a neural network that adaptively learns what each different bit string represents in number space, and then you kind of have a more dynamic machine epsilon that depends on some model. But as far as I know, there has been no such research yet. So machine epsilon depends, so far at least, only on the floating point or fixed point type that you decide to use.
Okay, thank you very much.
The same line, I mean, you have shown that the low precision floating point numbers contribute to errors, and they can be comparable to those caused by representational collapse or over squashing. What do you think? Could increasing the precision in just the final layers of the transformer can reduce the problem significantly if we use, let's say, approximate arithmetic in the earlier layers? Or are there alternative numerical representations, let's say mixed precision training or some sort of adaptive precision techniques that can mitigate the impact of this low precision, let's say, without compromising the computational efficiency? What do you think?
Right. So this goes more in the realm of lower level engineering, which I do have a basic background in computer science, but this is not an area that I'm an expert on. In principle, the answer is yes. So any kind of clever combination of precisions that you can measure doesn't make a big detriment to the training efficiency, while increasing the machine epsilon, will provably make all of these effects easier. Because our proofs say you can put the numbers below any epsilon you want. Obviously, the lower the epsilon you care about, the better time you're going to have, right? So anything you can do to improve that will make the situation easier. It won't solve the underlying problem, mind you, but it will definitely broaden. I guess it will improve the agentic capabilities of the model. Yeah, so it's going to allow it to do more things autonomously and require supervision for less things. But yeah, this could definitely be helpful. I would not be able to tell you how to do it. I just don't have that kind of engineering expertise. But in principle, yes. So anything which improves the machine epsilon is a good thing from the perspective of these results.
Another very intriguing point that you touched is the connection to over-squashing, actually. And let's say we have certain techniques to mitigate over-squashing in GNNs also, like let's say the residual connection or data message passing mechanisms. Can these be directly applied to transformers also?
Yeah, no, of course. So actually, residual connections can help delay a lot of the effects we're talking about here. So, if you want empirical evidence of this, just try training a transformer without skip connections. You're not going to have a good time. So basically, it is like, it's definitely important. It definitely delays the effect. But basically, the problem is that the effect is still inevitable on the level of a single head eventually. So, and we can observe this effect happening even in architectures which have skip connections. So it's like, it's a great, like, I imagine a lot of what we're doing now in transformer design is we're coming up with these clever tricks, right? Like you mentioned, the precision training or residual connections that sort of help delay when this effect will happen, so you can do more applications more reliably. But I'm personally interested in using LLMs to advance science. Like, I want to solve problems that we don't know the answer to yet. And you might need to think for a very long time or try many hypotheses before you get to the correct answer. The problem size that your model will observe before this happens can be prohibitively large, no matter how smart the tricks are today. And that's why I believe we need to try to move out of the realm of tricks and into the realm of more hard changes to either the architecture or the position embedding or something like this, if we truly want to solve big open scientific problems with these models. So yeah, that's like, for many applications, you can get away with the way things are now, as evidenced by the many great chatbots in existence today. But like, this doesn't mean research should stop, if that makes sense. There's many more interesting things we can solve.
Yeah, that is very encouraging for all of us. And another issue in the related area, do you think other graph neural network related phenomena, let's say like oversmoothing, can that might also manifest in LLMs due to these representational issues?
It definitely can. I am not currently in a position to tell you more about it, but we are preparing an ICML submission on a very related topic. So if you keep your eyes on the archive, maybe you will see some papers soon that talks about something very closely related to oversmoothing. So yeah, but definitely, yeah, because the reason for this, and maybe I should stress this more properly, is that transformers are graph neural networks. Like, they operate in a very weird way, but they do operate over pairs of tokens. So there is a graph structure underlying what this model is doing, right? And basically well, not necessarily a complete graph, can be a complete directed graph, right? Especially with modern decoder LLMs. Yes. Exactly. So essentially, any vulnerabilities that people in GNN research have identified will totally apply to transformers as well. And as we've seen in some of these papers, are sometimes exacerbated in transformers because of the weird shape of their causal graph structure. So yeah, totally. Any research, I mean, oversmoothing is one, but any research that people have done over the years with graph machine learning, I feel like sometimes LLM researchers are rediscovering things that we knew in graph machine learning land for many years. So, if any of you has expertise with graph machine learning, you can exploit that to make progress in transformers, totally. And many effects work just as you would expect them to. Yeah.
This is a great, intriguing fact you just revealed before us, and we were thinking of.
I have one question from the neural algorithmic reasoning. My question is, why should we learn algorithms? That's like sorting, insertion sort, or Dijkstra's algorithm. Why should the model learn the algorithm? What's the motivation behind the NAR?
Right. So the motivation I presented in this work is evaluation, right? So to be able to tell how good is your model class at generalizing outside of the distribution, you need to test it on a problem where you can even generate an out-of-distribution training set. And as I've argued, by definition, this means there must exist an algorithm which backs it. So that's kind of it's an evaluation motivation. However, the part which I did not have time to discuss in the talk today, but you can find, but you can find many of my previous papers and talks is about these papers like dual algorithmic reasoning or similar, where you train a model to execute an algorithm and then you deploy it in a real world task. Like say we train a model to execute max flow and then we deploy it to analyze the structure of the mouse brain, of the blood vessels in the mouse brain, which often relies on blood flow analysis. You can often pre-train a model in this algorithmic sense and then use it to solve a real scientific problem as a prior, because it allows you to apply the algorithm in the settings where the input features don't match what the preconditions of the algorithm are. So yeah, that's another really important thing that I didn't talk about at all today. Well, TransNAR is a bit of an example of this, where we use the algorithmic model to improve a transformer. But yeah, generally speaking, I believe these things are valuable beyond just evaluation. Yeah.
Thank you.
Thank you.
We have another question in the chat box from Devanjo. Can you kindly answer?
Just take the last two questions and then let's finish it.
Yes, finish it.
Okay, sounds good. So there was, so it was a question from Advai asking about using a shared graph space for our GNN model. And it asks, doesn't it make the model unaware of why we're using a particular data structure? So this is not completely true. Well, it depends on exactly what's the data you feed into the algorithm. And specifically, in many cases in CLRS, we don't feed just inputs and outputs into this model. We track the state of the algorithm throughout the whole execution. So if you use a linked list or an array or a graph, the features that the model is asked to predict in the CLRS actually match the way the data structure is being used. So for example, if you're solving MST using Prim's algorithm, you will learn how to maintain an ever-growing tree. Whereas if you're solving it using Krushkal's algorithm, both are inside CLRS, you are learning to maintain a forest, and you're also learning the edges of a disjoint set union data structure directly. So basically, the way the tasks are set up, you're actually explicitly learning how to use the data structures. So I think that information is not lost, though I'm very happy to debate that with you if you disagree with me. And as for Debanjan's question, which is first and last finding problem, it reminded them of languages accepted in the first order logic family. So there are works investigating which logical language families transformers belong. This is a really interesting question about which logical languages are expressible using transformer decoders. I actually don't think, I'm unaware of works analyzing the logical class of transformers, which also assume the causal mask. I know some really good works from Google research. You can look up Anton Tsitsulin. They had a NeurIPS paper recently actually analyzing the expressivity class of graph transformers, but I think they don't assume the causal mask. So there is actually, I think, an unexplored area of research for anybody who has like the knowledge in complexity theory and is keen to try to explore that. You could try to fill this gap, because I don't think it's been filled. No.
Okay. So thank you once again, Peter, for this wonderful talk in our winter school on deep learning. I would like to extend heartfelt thanks for delivering such an excellent and insightful plenary talk, and your deep expertise and ability to articulate the complex ideas with clarity actually left us all inspired and enriched, I should say. We especially appreciate the time you took to address the audience's questions with patience and depth, offering valuable perspectives that will undoubtedly spark further discussion and exploration in the field. And of course, your remarkable contributions has already set a high standard for intellectual engagement, and we are truly grateful to you for your presence. Thank you very much.
Thank you, Peter.
Thanks for having me. Hope I'll get the chance to speak to you again next year or whenever there's an opportunity.
Sure. We will be very grateful. Thank you. Thank you. Have a nice day. Bye-bye.
You too. Bye-bye.
Bye.